So I have a baseball, mass of the baseball, comes in about 90 miles per hour, bat hits the ball, leaves at about 90 miles per hour. Okay, so I went online and I found, okay, well, the ball's in contact for the bat for about a millisecond, 1,000th of a second. So what impulse did the bat deliver to the ball? All right, so impulse is the J. All right, so let's say you look in the book, you say, okay, I want to find the impulse. It's the average force times the time. Well, there's no indication up here what the average force is, okay? But that's where you have to remember that impulse, okay, is another word for change of momentum. Okay, and that's the example we just did, right? You can easily calculate change of momentum, P final minus P initial. Okay, so again, for this problem, here's my coordinate system. Okay, so P final is change of momentum is P final minus P initial. So factored out the M. So my final velocity is 40. Okay. Whoops. Well, my final velocity is 40, and I said it goes in and out with the same speed. So my final velocity is 40, and my initial velocity is minus 40 because it's heading to the right. That's my negative direction. So V final is 40, V initial minus 40. That's the mass of the ball. Okay, I put this in the calculator, and the impulse, right? The impulse that the bat delivered to the ball would be 12 Newton seconds. Okay, and since it's positive, it's to the left. Okay, now I could also ask, what impulse did the ball deliver to the bat? Okay, so in that picture, okay, if this is 12 Newton seconds to the left, then that would be 12 Newton seconds to the right. So this would be the impulse that the ball delivered to the bat. Just like Newton's third law, the bat exerts a force on the ball. Okay, here the ball also exerts a force back on the bat, and also exerts an equal and opposite impulse back on the bat. Okay, so that's for part A. Part B is, what's the average force that the bat exerts on the ball? Okay, well, you already know the impulse is a number, and the impulse is the average force times the time, so I can just solve this for the average force. So here's the impulse, there's the time. Okay, so that gives me my average force at the bat, and also the average force that the ball exerts back on the bat. Okay, but this is the average force that the bat exerts on the ball, and it's positive, so that means it's to the left in that picture above. Okay, now part C, is what's the average acceleration of the ball? Okay, well, I go back to the earlier chapter, F equals ma. So the average force is equal to ma average. Solve this for A. Okay, I know my average force, I know the mass of the ball, and I get a big number. Okay, does that number make any sense? Well, what I did is I took that number, 80,000 meters per second squared, and I said, okay, well, in 1g, I have 9.8 meters per second squared. So that says that the acceleration of the ball is about 8,000 g's. All right, now, does that number make sense? Well, here you have a ball coming in at 90 miles an hour, okay, and it changes its direction 180 degrees, okay, in 1,000th of a second and heads out at 90 miles an hour. So that's an enormous acceleration. So imagine if you were on some planet, there's you, okay, where g for that planet was 8,163 times g of Earth. Okay, so if you were standing on a scale, you would look down, the scale would read 8,000 times your weight. All right, could you stand on that planet? No, right? You would just be flattened because your body, right, can't withstand that shape because we're mostly water. We'd be flat. All right, but if you put a ball, okay, if you put a baseball on that planet, okay, the baseball would be deformed. Where'd that go? It looks like that. Okay, so that would be the planet, right? And this thing would feel 8,000, was it 163, maybe times its weight? Okay, so the baseball couldn't stay perfectly, couldn't stay perfectly spherical. Couldn't be like that. Okay, so the baseball would actually deform because the baseball's not perfectly rigid, right? It's got string, it's got rubber bands in there. Okay, so it's not like a solid metal object. All right, so that would make sense that it has such a huge acceleration and such a huge force on it that it no longer can remain spherical.